All right, good afternoon from sunny Perth, everybody. Welcome to Petra's first of two webinars on digital twin models for geometallurgical and materials handling indices, closing the gap between planned versus actual plant performance. My name is Leon Morgan. I'm head of partnerships at Petra, and I'll be your host for the next hour. It's really good to see so many people join us today. From across the globe as well, which is just fantastic. We have strategically placed 2 sessions to cover as much as possible after some feedback from our last time, so that's good. Really happy to see it. Our aim with these webinar series has been to effectively keep us all connected and information and innovation conversations, still being, keeping us in the loop. Just with us all stuck in home, it's good to keep going. And speaking of information, do you guys know that the earliest recorded name of a cat was 3,400 years ago in Egypt? Its name was Nedjem, and it means sweet or pleasant. And as James, one of our speakers, is from Egypt, I thought that would be a fun fact to start us off on, because there, why not? So today we will see a brief case study on Petra's MAXTA Geomet digital twin models, but the bulk of the hour will be a Q&A with the rest of the panel here. I imagine that after the last few weeks, everyone's pretty familiar with video conferencing calls. And with that, I just give you some house rules. So if you all don't mind staying on mute for us, that'd be great. At the bottom of your screen, you will see a chat button. If you move your mouse, you might have to pick it up, and you can ask everyone questions here. So just pinged everyone, so you should be able to see a little red dot down there too. If you ask questions there, myself and the panel will get to it as we progress through the day. So now, no one really is here to listen to me talk about cat facts. So with that, I thought I'd introduce our panel. So firstly, we have Professor Peter Dowd. Peter has more than 40 years experience in academic research, teaching, administration, and consulting in mining. Much of this work has been modelling and estimating of ore bodies, often in very complex geological systems. Also the generation of 3-dimensional ore body models as a basis of optimal mine design and scheduling and qualification of geological and technical risk association with reduced extraction, just to name a few. There's probably a few more there too. Peter has been cited as one of Australia's 100 most influential engineers by the Institution of Engineers Australia, and is the director of Australian Research Council's Industrial Transformation Training Centre for integrated operations of complex resources. I'm really surprised I didn't stumble over any of that. Peter's quite a perfect man, and I'm glad I got that one right, which is good. Secondly, we have James Carpenter. James holds a master's degrees in geostatistics from University of Adelaide, which he did under Peter Dowd, we found out earlier, which is nice. He has 17 years experience in mine geology, exploration, and resource geology. James is currently a senior research geologist working at Sukari, I think I spelled that right, underground mine, gold mine in Egypt. His previous experience included working with PanAust as a senior geologist as well, where he engaged Petra to investigate gold recovery at their gold-silver mine in Laos, something we'll touch on a bit more shortly. He's also worked at Olympic Dam, Ranger Uranium, Cap Coal, among others, and we're really excited to have James join us today as well. Lastly, we have Dr. Penny Stewart, founder and CEO of Petra. Penny worked on mine sites for 5 years before obtaining a Queensland first-class mining manager's certificate in competency. It was during their time here, she worked in the underground and open pit mines in WA, where I'm at, that she learned how geological uncertainties affect our ability to mine to plan. This experience led to a study in the mechanical behaviour of rock as part of her PhD studies at UQ's Mineral Research Centre, where she developed statistical analysis and modelling expertise at a time when most people were more interested in applying numerical modelling. In 2015, Penny founded Petra 5 years ago with the hypothesis that engineering behaviour of rock throughout a mine, is best estimated by feeding back hundreds of millions of tons, my mistake, of actual mine performance data into engineering models and optimizations. 5 years later, Petra's flagship product, which you'll see more of in a moment, MAXTA does exactly that. So if you could please join me in thanking our speakers, which is good. You're all muted. I'm assuming you're clapping quite loudly. Thank you. So with that, I'll happily pass over to Penny for a quick presentation.
Thank you very much, Leon. I've just got a 10-minute presentation that I'll share with you now, and then we'll be back into the Q&A. All right. So today I'll be mainly giving you a quick summary of what we mean when we talk about MAXTA Geomet and how it feeds into providing more accurate mine planning and inputs for mine planning and for mine optimisation. So the purpose is to increase productivity in the mines by increasing the accuracy of mine planning and optimisation. And that has two main applications. One is in operations, which is the one most people think of straight away. And that's about closing the gap between what you plan to do and what you actually get. So that's one side of it, but it also has an important place in the whole studies area as well. And that means that when you go to do your feasibility or pre-feasibility studies, that you're able to get better estimates, and therefore your NPV and economic analysis is also more accurate. I'm just going to move this little video away. It doesn't want to move. Okay, so how do we do this? The main thing what we're doing is we're feeding back actual performance into the block model and relating that back to the geology, and we do that by tracking the ore throughout the whole mine. So a large part of achieving these feedback loops into mine planning is actually the ore tracking side of it. And so quite a lot of effort goes into the ore tracking, whether it be tracking through stockpiles or crushers or whatever other part of the value chain. So when we talk about a digital twin model, what am I meaning by that? I mean it's the integration of data and spatial data as well, and integrating that with mathematical models to enable you to simulate and to predict and to optimize that virtual representation. So the model is like a virtual representation of the real world, and it's connected into the real world through some sort of often live connections, but it can also be connected by, real data flows as well. It doesn't have to be in real time. It can be also in a timely enough fashion. So like with the block model, you might not have a live connection into the block model updating all the time, but the time whenever you do update your block model, it will also update the predictions, for example. So why would you want to have a digital twin? There's a few main functions that we're talking about today. Is the prediction function. So that's the ability to predict and prevent production losses or downtime. That's the main purpose of MAXTA Geomet. It's about improving predictability and estimation. You can also use a digital twin for exploring what-if scenarios. So that's where the model is used to ask a question. So you say, if I change, and we use this in drill and blast. So the last webinars that we ran were in the drill and blast space, and that's where we then use the model to say, if I change my burden or my spacing, this is what effect I'll get downstream. And then finally, the final bit that you can use a digital twin for is to ask the question, how do I achieve my best performance? How did I do that historically? So that's mining the data to say, when I did this in my operation, in this geology, I got my best performance. And that's the, how can we repeat our best performance 24/7? So I'll now move into some case studies. And the first one I'm going to talk about is the case study that James Carpenter is most familiar with. And in fact, it's referencing a presentation that James gave at the AusIMM's Complex Ore Body Conference in October 2018. It's PanAust Banasai mine in Laos, and we deployed a geometallurgy machine learning model into the block model, and it was based on 10 million tonnes of historical ore data. So I'll just give you a bit more information on this case study now. Banasai is located in the Laos People's Democratic Republic. It's been in continuous production since 2012, but I understand that it has been COVID has affected that site, so it may not be in production right at this time, I'm not sure. The amount of data that we used there was 2 years of historical data from March 2016 to March 2018. It was about 10 million tonnes. It's an open pit mine with direct tip and to the crusher. And there was around 5.12 gigabytes of data that was consumed by the software. I hope that you can see the video okay, but it's a zoom footage flying over the site. We've just flown over the plant. You can see the ROM pad down there. It's about to switch over now to a block model view. And what you'll see is the pink and red blocks are the blocks that, based on the historical mining or the machine learning models, these were the blocks that were highlighted as having low recovery associated with those areas. So we were able to predict where those areas were without any knowledge of where they had historically had that issue, and that then when that was put back into the block model, that showed good agreement with their experience at that site of having this recovery problem. So that new method of doing prediction was then used in the whole life of mine planning process as well to predict areas which had high tails areas, and high tails meaning high tails grade. So the machine learning model was a model to predict high tailings grade, which is obviously related to the recovery at the site. That's the first case study. The second case study is a mill throughput prediction model, which was deployed into a block model for mine planning and blending purposes. And this one, again, was based upon 2 years of data, and they were using this block model predictions. You can see the stratigraphy there, and it's showing basically the high throughputs are shown in the red and yellow, and the lower throughputs are in the cooler colours. But they were using it for blending purposes. So they had a very high variability in their throughput in these mills. And so they were able to use the Geomet predictions in the block model to improve their blending and get a more even performance for the mills. Well, not just even, but by smoothing out the blend, they actually got an overall increase in throughput. So what do these, I'm just going to take a minute now to explain the models that go behind this. We've fed in, tens of millions or up to hundreds of millions of tonnes of ore through the ore tracking, and we've built a database that we've then related back to that geology that we've tracked. Once you've done that, we build a machine learning model. And what we do to make it more, because if you don't provide any visibility on those models, it becomes a black box, and people just see a prediction in the block model, but they have no insight or no ability to extract more information from that. So what we also do is we provide people and users of the with these plots, and this gives you sort of an idea of the interpretability that is available through machine learning now. These are called SHAP plots. And what they do is these are all the block model predictions that went into that throughput model. You can see them there. They're typical sort of fields that you would see in any block model. And what you can see is that when it's high, red, that means you're getting an increase in throughput. So the ones going to the right, you're getting a higher throughput. There you can see here, this is the SHAP value. So when it's gone this side and it's high, that means you're getting an increase. If it's blue and on that side, that means it's low and it's going down on that side. So this gives people an ability to see what's going on inside the model, and we call that a glass blocks. And it's important to mention this because when you go to deploy these models into production, people will want to have some level of visibility on what's inside the model. All right, that's what I had from the demo, so I will hand back to you, Leon.
Thank you, Penny. With that, I'll just kick into some questions for the group. But before I do, I might just invite perhaps Peter first. Is there anything you just want to add as general thoughts to the topic as a whole?
Yeah, I won't concentrate on digital twins, except to say that, of course, PETRA Data Science is involved in the new training centre as is the salt system, so we can expect a lot of digital twin performance characteristics in what we're trying to do there. My experience, I suppose, is with the Geomet data itself, and most of that work is really dealing with problems. The fundamental problem is that geometallurgical variables are costly. So in mining operations, you get very few of them. They're not additive. They're not representative of the entire mine or the entire ore body. And the difficulty with all of that is dealing with insufficient information, which artificial intelligence, machine learning could well help interpreting, but also trying then to integrate that with directly measured data such as grades. How do they affect that? And that, in the work that I've been involved in, has been a fundamental barrier to any meaningful output from modeling geometallurgical variables.
Fantastic, thank you, Peter. That's a really good instance. And just to you, James, as well, any initial thoughts? And I've also got my first question for you as well. I might ask at the same time, because you were part of that PanAust work that Petra has done that was mentioned in the case study. So I'd also like to probably start by asking, what were the impacts and the value of doing such work in this manner, and how did that relate to further mine planning and so forth?
Well, as Peter said, geometallurgical modelling is has its unique challenges. We obviously tried to work out what was going on and what was causing this impact through test work programs, and it really was not giving any clear results. And the approach that Petra took was to use the actual plant performance, and the plant itself is the testing device. And basically that just gave us an immediate feedback because we'd already mined it, and you know, it's quite real. It's what's happening as the material goes through the plant. I was pleasantly surprised on how well everything went with the project with Petra, and yeah, just to get a clear answer at the end of it. Obviously, we had a very long list of correlated variables, which correlation doesn't mean causation. So we did have to put our thinking caps on and think about what exactly it is in the geology that was causing this. And so it's not just machine learning, it's also experience and knowledge, geological knowledge that you need to get these sorts of projects to be successful.
Yeah, no, that's a very good insights around domain knowledge and understanding, because with just data, you have just data, you know. It's sort of innate. So I guess I might start quite high level as well, keeping with yourself, James, even, is why do you think, and Peter obviously joined in too, why do you think we need to improve geological ore body knowledge as a whole through a macro level over the actually entire site?
I'll start if that's all right, Peter. The whole point of this is, you know, we're all split in departments here on the mine site with the geology, the survey, the mining engineering. But what actually benefits the business overall is to have some fairly basic things happening, such as good throughputs through the mill, only feeding the material which is economic, and it's very basic on the highest level, and quite often there's no one department which is overseeing what's best for the business. We all work together, obviously, but you know, basic things like increasing powder factors to increase mill throughput. Quite often there's a budget on the explosives that we use here, and to have a digital twin which we can use to pull a few levers, we can demonstrate that, say, increasing the budget for drill and blast may actually save the business a heck of a lot more money than what it costs to put a bit more info in the ground. So the integration and the looking at the business as a whole, I think there's a real benefit in these sorts of programs that Petra are developing.
So that's actually a good segue into my next question here, which is how does geometallurgical and materials handling performance affect investment decisions? Because it's one thing to understand needs to be done, but and you spoke about increasing budgets and so forth. How is that all sort of combining?
Well, I think certainly at a feasibility stage, there's no digital twin, and I think the sampling school, which I'm very interested to hear more about from Peter, that's very important at that stage. In fact, if it's all right, can I hand over to Peter?
Yeah, go for it, of course.
Oh, I suppose the short answer to the question is profitability. You might also put in contributions to environmental sustainability as well. Why process rock that is not going to increase your profit when it will also use energy that could be used usefully elsewhere? It's part of the whole concept of optimizing the entire value chain in a mining operation. And it's certainly in my experience, it is the one element that so far, largely to date, with maybe the exception of what you're doing, has not been achievable. How can I characterize the characteristics of a rock mass in terms of the entire processing value chain, along with maximizing the grade values? And it's that is a fundamental research problem.
So speaking on that, and I think you bring up a really interesting point there, which relates to license to operate. So you're talking about, using energy and efficiencies and so forth. And our license to operate in this industry is changing from not just safety, but to environmental concerns.
Yes.
I think that, how do you think we will move forward into that world using like current techniques, for example? How does what's been done, how do we need to evolve is what I guess I should ask there.
Well, I think in a way, a lot of what we need is already being done. So if again, I'll introduce this training centre that we've just got funded from the Australian Research Council, with about 20 industry partners involved. The idea here is to look at the mining operation as a completely interdisciplinary problem. We're very good at taking parts of the problem out and optimizing it and putting it back in, but it doesn't necessarily optimize the entire entity. So in that respect, anything that we can do to increase that knowledge as we go through the modeling and the prediction and the management will improve things. And the answer is sensors. We sense data all the time, but for example, if you go to most mining companies and you go to a core yard and ask whether the core was sensed, more often than not, yes, it was. But it took so long to interpret the values that the opportunity to use the information has passed. So what we really need is to be able to sense in real time, integrate sense data and directly measured data in real time to make real-time decisions. And that's fundamentally what the training centre is all about. And I suppose it's fundamentally what most companies, maybe not, they wouldn't express it in those terms, fundamentally what most companies really want to do. And your digital twin, or anyone's digital twin, I suppose, enables you to do that in real time. But to do it, you must have the information flowing in real time and being able to update your resource models, update production models, and so on in real time.
So with that, Peter, what do you think is the next big impact that will happen, and where do you think will this be? I mean, to tackle the whole problem at once, is that the next play, or is it to we don't want to pull out parts of it, but we've got to start somewhere? Where do we start?
Well, as I said, that is what we're being funded to do with the training centre. PETRA is a member of the training centre. It is to look at an operation holistically, not as a sum of independent parts. So that is a concept in its own right, but the ability to do that depends upon being able to collect and use data in real time. And they're the big research questions.
Yep.
So in 4 years' time, when the training centre comes to an end, I would hope that not only the 20 industry partners that are involved in this will have the answers, but we will provide something that will go out into the wider field that will indicate how this could be done.
Penny, you had something to add?
Yeah, I just think it's a really good point that Peter makes about the eventually getting to the live digital twin. At the moment, I think I said we remine the data. We use the ore tracking to remine it. It's not actually due to a lack of sensors necessarily. In our experience anyway, that sensors are certainly valuable, and the more sensors you have, the more fidelity you get in your data. But in our experience, the challenge is actually making all the connections into operations in a reliable 24-hour, 7-day-a-week fashion. And the cost difference to go from a historical digital twin model that you built using that data and then step up to live digital twin, we've gone through that process of costing it for customers. We've got one customer who's currently looking at that option. We've built it, we've done the whole design, the software, architectural side of it, but it's quite a jump to go to a live digital twin because of all the connections that you need to make from a software architecture point of view. It's not necessary. I mean, I do think there's a place for improving in sensors, and I know that university research in the area will definitely add value, because there's certain areas where we lack fidelity of data, or the quality of data isn't as good as it could be, and those sensors will be important addition to it. But I do think there's still an ability with the current sensors that are available to get to actually go to live digital twin already. So I guess I just wanted to add that point, that we can do that now. It's just more about the investment in the software side of it and the architecture required.
So I think that raises an interesting point, and something that we spoke about just last week, Peter, around the data that we do collect at the moment and data sets that we do have in current testing methods. How reliable is that, and how much can we defer when we start to use these sensors and collect data in a new way, so to speak?
Yeah, I suppose any way of collecting data has some uncertainty associated with it. The way to address that, of course, is to take all that uncertainty into account when you integrate the data. So, for example, if we say that a laboratory assay of a core is reasonably accurate, and that's probably true, then how do you treat the level of accuracy of that information with something that is being streamed to you live as a sense signal, and that signal is measuring something in some way, and you've got to extract from that signal what it is that you want from it, the measurement it's doing. So, for example, sensing things on a conveyor belt, sensing ore as it moves past a sensing device, will have a much higher uncertainty associated. How do you integrate all of that? And you could talk about this if we're using, say, some sort of tagging system in rock that has been blasted, following a material through the mining operation, together with other characteristics you're sensing all the way from in situ through to the concentrator. So I agree with Penny, it's a matter of being able to integrate all these forms of data, extract the information you need from it, but integrate it in such a way that you are correctly weighting the different elements that go into it.
It actually leads into something Luke here has asked as well, which is a really good question in my opinion. And it's around sensor noise, and how do we measure and understand that noise? And I know that Peter, you might have some thoughts on this. I know Petra, we do a lot of work on this as well with sensor work here. Do you have anything to add on that Penny?
Yeah, it's a really good question. It's one that comes up a lot, Luke, so thank you for asking that question. What we do is one of the limitations of a machine learning model is that you don't get the same statistical error metrics that you get from a statistical model. So what we'll do is we'll build a machine learning model, and we do a training and testing phase. So you have a training model phase, and then you subset a section of data that you'd never used in training it, and that's the test data. And you report on the accuracy of that test data, and that test data has never been used to build a model. And we have some benchmarking of what the accuracy needs to be for those models. And yes, you're right, there's some level of noise. And so that noise comes through in the modelling as errors, typically in the range, depending on what it is, anywhere from a couple of percent through to, say, maybe a maximum of 15% noise, average error in those models. Now, the thing about a machine learning model is you can't quantify the confidence limits. So when you have a statistical model, you can see the confidence limit. So you can see you've got a line, like many of the people on the call here are either geos or engineers, and many of us will have built like a simple 2-parameter linear model. And you can plot on there a confidence limit on that model, and it will show you where that line is, a 95% probability that that line lies in this area, okay? So what we do is we will always build a statistical model as well, and that will show us the confidence we have in that basic statistical model. The errors on that model are a lot higher because machine learning models are a lot better. So we'll typically reduce our error by about 40 to 50% when we go from a statistical model to a complex machine learning model. But going through that process of building a basic statistical model gives us an ability to quantify the confidence we have in the model. Okay, and that means you've got like a 95% probability confidence limit on the model. So that, I hope that answers a little bit about the scatter and the noise. Do we need to build that into a live digital twin model? In my opinion, you can build it in, and we do. So a good example is in a processing plant, you'll get drift in online analyzers. They'll drift. So typically they need to be calibrated. Now that calibration, if done offline, is quite a laborious, time-consuming process, but you can calibrate live. And so we have algorithms within this is for a processing plant, so it's MAXTA process. We have algorithms that automatically calibrate the data to handle the fact that you get drift in sensors. Can you do that live, in real time? You can't quite do it in real time, but you can calibrate every shift, for example. So when you get the assay result come back at the end of the shift, there's a bit of a delay to calibrate it. But once you get the assay back, you're able to calibrate that online analyzer, and then everything sort of resets and you can keep going forward. So there are ways of live calibration and fixing the data in real, not quite real time, but in a practical time frame that is valuable and useful for a mining application. So that would be my answer. I'm pretty sure Peter will have something to add to that too, actually, and maybe James too.
I agree with what you're saying. The other aspect of it is everything that we measure in geology and mining operations is a measurement for a specific volume. So if I took a core that was 1 meter in length and I assayed the entire core, that grade relates to a cylindrical volume of length 1 meter. The question then if I send signals into the subsurface of the Earth or on a belt or anywhere else, what volume is it I'm measuring? And if I'm going to combine the two, I must have some indication of what that volume is. Now, a lot of work in this area has been done in the petroleum industry over the past 50 years. So we know broadly how to do this from a direct point of view as opposed to machine learning type things. So we can deconvolute. If you think of it, the signal penetrates the rock to a certain limit, and what you've got is the product of the distance of penetration times what it is it's measuring. To bring that back to a common volume, you can go through a mathematical technique of deconvolution to get it back on a fixed volume. And that's part of the data integration process in all sorts of applications, mainly in exploration, certainly in the petroleum industry, less so in mining. But the same thing applies to the work that we've been doing on static volumes. If we're going to integrate the data, you not only have to account, first of all, any data you collect has got information in it, irrespective of the amount of uncertainty. So you wouldn't throw it away unless it was totally uncertain, you couldn't get anything out of it. The point is, integrate it with the other data, but take account of the relative uncertainty, but also take account of the explicit or the implicit volume that's being measured.
So a good answer, Peter. James, do you have anything to add there as well?
I do. It is a bit specific, but when it comes to sensors in the plant, the operation in Laos had around 2,000 different sensors throughout the plant, and they were being recorded in a process historian. They were using a software called Pi. And for example, a large motor which may pump the slurry from one tank to the next would have 7 sensors in it. And when it comes to actually integrating this into a model, you've got a lot of choice on which sensors you actually use. And there can be indirect sensors which mean something but don't directly measure. So the throughput, for example, you may find less scatter and less noise and variability in a particular pi tag, which is indirectly measuring a certain thing that you want to know. Another example is machine hours. It's a story I heard. Instead of manually reading the machine hours on an excavator, you put a vibration sensor on it. Mm-hmm. Obviously, if the machine is running, it'll be picked up by that. So we are collecting an awful lot of data at the moment, and it is possible to actually sift through and sort out and find indirect measures of what you're interested in as well.
Really good input there, James. I quite like that. We've got some. That's a good point. I've actually got one from Matt, which is fantastic and leads into this really well. It's come through privately, so I'll just read it aloud to everyone. As we move into real-time data collection and semi-real-time decision-making, what role does the mine plan have in decision-making? It is a constraint preventing the potential instantaneous value driven by traditional mine planning processes. So I think I might hand this to Penny. So at the core of this is, what role does the mine plan have in line with, as we move towards this technology shift, in understanding and lining that up with the geology of your site?
Yep, okay. Thanks for that question, Matt. It's a good one. What I think we're gonna see more of going forward, and we're getting asked for this by our customers actually already. Now they've got the ability to get plant predictions into the block model, people are starting to say, how can we then play that forward so we can see scheduled periods? So it might be your daily or your weekly or your monthly, and play that forward more like making the mine more like a processing plant. So you start to see what your predictions are over time. Now, I know mining engineers and geos within the mine have often had some level of visibility, especially obviously on grade. So you'll see grade and predictions on a shift-by-shift basis of what they're expecting to deliver to the plant. And the same, perhaps, there might be some mines which are more advanced and they'll have some estimates around throughput or some other factors. But I think what we're going to see more and more of is visibility going up to other parts of the operation. And Peter talked about this before, about we need to, talk about this new centre, the training centre. They're no longer going to have mining engineering, metallurgy, geology, all people working in silos. They're really focused on having people get more interdisciplinary training in their degrees so that they can understand these problems at the whole operation level. And that includes providing visibility on the impact that the schedule, the mine planning schedule, has all the way downstream. And we now have the ability to play that forward so that people in the plant can see what they're expecting to get. And even the executives at the site, in the past, they would, they get the schedule from the mine planning engineer and everyone goes, okay, that looks great. But there's not really how's that going to affect the plant aspect to that schedule. So once that's possible, and we're seeing that it is through these machine learning models, then the GM can go back and say to the young, usually quite young, scheduling engineer, junior, can you please try a different schedule because we really don't want to see the throughput in the plant drop by 20% this week. And so there's an opportunity to provide a higher level of supervision of what the junior mining engineer who's doing that schedule has got planned for the whole operation. And I say this from my own experience. I mean, I've been that junior engineer on site, making those decisions, deciding which block the whole mine is going to, this is a super pit. I was only like 27 years old and I was deciding basically what was going on across the whole value chain at that site because I was choosing which blocks they mine. And, I was totally blind to what that was going to do to the plant. So it comes from first-hand experience, actually.
Good answer. Penny, anything to add there, gents?
I think if I get reborn later in life, I'll definitely try my hardest not to be a mine planning engineer. It's certainly a very tough job, and yeah, I do have a fair bit of sympathy for the difficulty of the task. I think the idea that having a digital twin beside you, or running it through a digital twin to see what the future holds with this particular plan is a very useful thing to have beside you, and you can anticipate the issues that you'll be facing or trying to solve.
Yeah, fantastic.
Yeah, I think.
Go, Petty. No, go ahead.
Maybe just phrase that in a slightly different way. Rather than asking what role does the mine plan have with all these new data collections, why don't we say what role do data and data analytics have in improving mine planning?
Ask not what your mine plan can do for you.
Exactly.
I've got two good questions here from Ben Berger, great name, and Caspar Stopforth, which I'm just going to combine here. So I think they're on the same thing. So it's around operator limitations and poor performance in equipment use, and identifying these manually and building them into the model. So I think this is parts for you, Penny. But then also, Caspar's asked about a process to identify missing sensors and essentially sensor health. And critical towards a digital twin, but maybe not critical towards the process. If you see those, I think they're sort of one and the same almost questions around sensors.
Yeah, I think this is a good point to mention that when we build a digital twin at the moment, because there are issues with the data, we won't use everything, so we don't have to. I mean, if the mine's running at 60 billion tonnes an annum, and some of that, 10% of that data is fraught with issues. There might have been a shutdown, or there might have been some other weather issue, cyclone passing through that affects that model. We can remove that data, and we can still build a really good model on 90% of the data. So that helps with some of it. The question Ben's asked there in the chat is more around operator variability. It's a really good question. With a Geomet model, we don't have the downstream operator variability, and so that does come out as noise in the model. So that's why in a Geomet model it's not uncommon to get like 10% average error in a Geomet. That's over if you're trying to do it over a shift by shift basis. If you then apply that same Geomet model on a week by week basis or a month by month basis, you remove a lot of that noise and the accuracy goes to around 1 or 2%. So when you're trying to predict and see the predicted versus actual on a shift by shift basis, you'll typically see like more that 10% error, and that's due to the operator variability. But when you do your reconciliation on a week or when we reconcile it on a week or monthly basis, that error converges down to, or it gets much lower, and you get down to like a couple of percent. On like say a mill throughput, for example, we've got a model at the moment that the site just did a big reconciliation over the last 6 months, and they found that month to month the predicted versus actual was between about 0.7 and 1.9% variation from what we predicted in the Geomet model. So I hope that answers your question, Ben.
Yeah, fantastic. My next question I like from Greg, which I always like when someone asks a question that I had as well. It saves time for me, shouldn't have asked. And it's around thoughts on adding value to major decision making for the entity it undertakes. So I guess this also comes back to where else can we use such technology and digital twins like this to essentially create efficiencies, and how does that relate to things like iron ore prices written here?
Peter, how about you have a go at this one? I think it's in your space, isn't it? Or James, either of you would be onto this.
Yeah, I suppose if I use the training centre again as an example, it is initially focused on IOCG type deposits. So the end user partners are BHP and Oz Minerals. And the aim here is to look at, as I said, the entire process as some integrated process, rather than looking at individual components of it. So, again, I'm not sure what the question was asking in that context, but can you repeat the question again for me?
Oh, sorry. Any thoughts on how information around the digital twin can add value to major decisions within the entity itself? So, and he's used a specific example here around iron ore pricing over the last few years.
Yeah, we don't go into the sales part of it. We're limited to from the ground to the final, in the case of the two ore bodies concerned here, in terms of final concentrate for shipment. We're not looking beyond that in terms of prices and how the market operates.
Okay.
So I think it's an answer to that.
Okay.
But I suppose once you've got it up and operating, you've got everything that feeds into the market. So you need something on the end of that that, I don't know, simulates or predicts what is going to happen with better concentrates being shipped, or in the case of iron ore, better blends being met for customers and so on.
Okay. Anything to add there, Penny, around things like using these things for other parts of the business?
Yeah, look, I think this is a point where I would say you're getting into the optimization space. So not all digital twins look at optimization. We do have optimization layer on what we do. It doesn't do all types of optimization, and there are certainly better NPV optimizations for longer term time horizons. But the principle is there, and that is that we're just getting some noise from one of them.
That's all right, we're good.
Okay. Yeah, so that optimization means that you can add in things like iron ore price into that, because that affects like what the value of you increasing throughput is, say through a crusher. So we just did one for drill and blast optimization, and depending on the market condition, if you've got a high iron ore price, then you're going to hit production as hard as you can, and it may, well, not necessarily as hard as you can. You're going to optimize it. You're going to push tons, right? That's when high prices are high, people push tons, but they don't look at the cost side as well, and they don't look at efficiency, and they end up losing efficiency. And that might be okay when you do an NPV optimization for that scenario, but in a year later, if the price has dropped by 50%, and that can happen, then it becomes more about efficiency and cost effectiveness. And so then the optimization will push more about like reducing your cost, but you don't worry so much about loss in productivity. And those things we can currently model in our optimization, but there are better packages for doing we look at it for a particular business case at this point in time. When we do our optimization, there are obviously, one of our partners, MAPTech, has much more complex multiple time horizon optimization where it maximizes NPV, looking at the whole life of mine. And in that case, you're able to model much more complex economic scenarios. But I would say that question is leading into that mathematical optimization side of things.
I hope that covers you, Greg. I think it was a great question, mate. We did have a message earlier about the details on Peter's training centre as well, and I'll make sure that gets circulated after this so people can have them on hand. Steve Sullivan's asked an interesting one here around bringing the mine planners along for the ride. As decision makers, they will have to make better and more timely data, which to make strategic calls. I think that that leads to the question around implementation. How do we get take up? How do we get people to use this? I might ask you, James. So you've seen the value of this type of projects and so firsthand. I think that how do we influence upkeep and uptake of this?
I think what you're doing right now, Leon, is perfect. Is to share the information, have a demonstration of an industry example, and yeah, it's just I'm just hopeful that the higher levels, the executive committees, get word of this sort of capability that is being developed. I'm extremely heartened to see MAPTech is working with PETRA, so exposure through software programs, And yeah, I think it's just got to grow organically, and you know, it's good to hear and have these sorts of webinars.
Thanks, James. I'm blushing. Anything to add on that, Penny or Peter? Just on upkeep.
I think.
Peter?
I think most medium to large mining companies are already looking at this. The question is, once they've finished funding research for it, will they actually implement it? But certainly, there is no shortage of companies that are requesting research in these areas.
Yeah. Yeah, I guess that question about you've raised, Peter, and about the implementation and the uptake, I think our friend there, James Carpenter, has been quite modest. He did an exceptionally good job of getting the stakeholders aligned, getting it communicated remotely. Like, this site was in another country. He was based in Brisbane, and he managed to get people on site to get the data in a timely fashion. He managed to get the people to use it. We've seen quite a lot of these projects now over the years, and some of them are executed extremely well. And I have to say, James, yours is probably one of the best ones we've seen. And then some of them, they may have an extremely good technical outcome, but they're not able to, for whatever reason, get it into production, which is really amazing. So I do think that getting people who can affect change, like people like James, and understanding what their secrets are, is a hugely important in mining. And I don't know if we're doing enough fundamental research into that, actually. I'd love to see fundamental research in how do we affect change in mining. Why is it sometimes we're so successful and we have these amazing outcomes, and then the same technological outcome, but we get a totally different value result? I would really love to see that kind of research done at a fundamental level.
Got any PhD Peter that are looking for something?
Well, I didn't hear that.
I'm just saying, PhD students looking for a topic?
Well, there are 16 PhD projects in the training centre, and the topics were largely fleshed out with the industry partners. So it's what they wanted to come out of this.
Yeah.
Fantastic. Is there anything on there that relates to today's topic, for example? Anything that's you think is pressing for industry right now that your training centre is going to tackle?
Well, obviously, the two large mining companies that have joined up have already decided what it is they want to tackle. But it is to look at the operation as an integrated whole, and it's to use data analytics, digital twins, integrated extraction simulators, whatever you want to call them, to build a holistic approach to a problem from beginning to end, and not break it up into individual components. Now that's hard in an industry like mining to do. Traditionally, you have a geologist, a geology department, a mining department, a processing department, and they certainly when I worked in the mining industry, they operate as independent entities, and the problems get thrown from one to the other, and rather than looking at this as an integrated operation. I suppose you could look at what's happened in the manufacturing industry to show what benefits have arrived by looking at things as an integrated system. It's been much more difficult in mining, but the message has certainly been received, and it's certainly being acted upon now. Not just here in Australia, but all around the world. Large companies are investing enormous amounts into this type of concept, using the Internet of Things, using ubiquitous data collection through sensors, integrating data and making decisions in real time.
Fantastic. Great. So we're in the last home stretch here, guys. So I might just ask, since James is back from his production problem that he fixed quick smart, which I did notice, mate. I might start with you, mate. Any final thoughts you want to share with everyone?
I think digital twins, data, sensors, all these things are important, and they are useful, and they can deliver real value for the operation. I think leaving an operation to run as it is not sort of in a lot of our sort of the way we work. You know, we like to improve and get things better, and there's great satisfaction in that. And you know, this is just a a good way to go about that. You know, the optimization and certainly using the data that we are collecting in a more sensible way. We're not necessarily looking to spend more money in more assays and new hyperspectral scanners. Quite often we have enough data that we can, if we put it all together in a sensible way, we can use what we have right now to improve our business.
It's a great point, man. I think that's at the core of PETRA as well, which is how can we use what we've got to try and create some meaningful, impactful projects, which is fantastic. Peter, any final thoughts from you, Peter?
No, I think I've said all I wanted to say.
I'm glad to hear that. I'm glad we covered it off. That's good to hear. And Penny, what about yourself? Anything left?
I guess I would comment a little bit on the differences between mining and manufacturing, if I could make one last comment, because it's something that has come up a lot in mining lately. I hear people talk about manufacturing and relating it to mining and saying that we should be like manufacturing. I would say that, and I'm sure Peter is totally over this too, because he knows about the importance of geology, but we can never lose sight of the impact of the variability that is intrinsic in ore. So geology, and I know I'm preaching to the converted a little bit here because most people on the line understand this, but the more that we can learn how the geology in all of its complexity at different scales affects each of our processes along the value chain, the better we're going to get at executing what we want to do and that plan, okay? Now, applying a manufacturing digital twin to mining, assuming constant engineering mechanical behaviour or the properties that we, in a normal manufacturing plant, people know what the inputs are. They can quantify, they can measure the strength of steel, they can measure the performance of an electronic component, right? These are well-defined engineering characteristics. But in mining, the engineering behaviour of what we deal with, which is the ore and then eventually the slurry, is extremely hard to quantify. And I think it's as we get better at doing that, all the way through the value chain, we're going to see mining become as the aspiration that Peter's whole centre is built on, that aspiration of integrating and optimising across the whole value chain. A fundamental part of that, in my mind, is the ability to track the ore right through that process, all of the ore. And as you're able to do that, and as it hits the plant, and you can track the slurries, and you can see how that particular ore is going to behave at that point in the value chain, that's when we can start to really integrate and optimise across the value chain. So I just wanted to make that point. I hear it a lot about the whole manufacturing analogy to mining, but I do take some issue with it because it does devalue a little bit the impact, the fundamental problem we have, which is the variability of our inputs, which is the ore.
I think it's a really good point, Penny, and I don't think we should discuss it with Dassault Systems too much about the difference between manufacturing and mining, but I think it's a really good distinction that needs to be made. Great. So I might end it there. Thank you, everyone, for joining us. Thank you to our lovely guests as well. I do invite everyone to stay on the line and share video and continue the discussion as well, potentially for another 20, 30 minutes. You're welcome to ask any other questions you might have outside of this. But thanks again to everyone, and please enjoy the rest of your day.
Thank you.